Hello, in this video we're going to discuss a very useful data structure which is called the stack. We are going to talk about some examples, computer applications, and also the methods that we need to implement when we decide to use a data structure called the stack. This video we're going to discuss a very common and useful data structure called stacks. And you're going to see that this is different from other data structures that we have been using so far. For starters, this is what we call a LIFO data structure, LIFO, which stands for the last item in is the first out. LIFO, last in, first out, LIFO. And that means that the last value that is added to the collection is the first value that is going to be deleted. And notice that we don't pay attention to where we add. There is only one place we can add, and we don't need to know neither the value nor the position of the value that we want to delete. The only option that we have is to delete the last item that was added. So some examples is anything that behave in real life like a pile. So we have a pile of books. Think about it. If you want to add books to the pile, you add the books on top of the existing pile, right? And then when you want to pick a book from the pile, you pick the book that is at the top of the pile. So we add new books at the top of the pile, and we remove books from the top of the pile. And the first book to be removed is the last one that we added. Last in, first out. The last added is the first one to be deleted. Same thing happens when we have dishes to be washed, right? So we are in the kitchen sink, and we have a pile of dishes, and then we grab the dish that is at the top. But probably that was the last one that was added. So basically, as I said, anything that behaves like a pile could be represented using a stack, and in real life behave like a stack. So now that we understand that the insertions and deletions take place at the top actually is a name that we use currently when we talk about stacks, and it's very important. So the top indicates the location of the item that was added last and the item that is going to be deleted. This happens to be very convenient because as we're realizing, the stack items, the stack values are not organized in any sort of order. They are not in increasing order. It doesn't make any sense to sort the stack like we do with other data structures. These values simply are inserted by position. So we insert one on top of the other. And basically, the only one that is relevant is the last one that we added, the one that is located at the top. So when we discuss the operations on the stack very soon, you're going to see that all of them happen at the top of the stack. So top is a very key word for the stack. So what are the stack's operations? So it makes sense, obviously, to initialize the stack. We're going to have to use some sort of implementation, so we need to initialize implementation, and we'll discuss that in detail later on when we talk about the implementations of the stack. Obviously, we need to insert and we need to delete. Okay, insert has a very specific name. It's called a push, and deletions have also a very specific name, are called pop. So when we talk about push and pop implicitly, we are talking about stacks. And when we talk about push, we were talking about adding an element to the existing pile. So in a sense, we're pushing down the existing elements that are already in the pile and placing the new element at the top of the pile. The remove method is called pop. And again, think, you have a pile, and what we do is we popped out. Okay, we popped out the element at the top. So we push new elements onto the top, and we pop elements from the top, one element at a time. As in any other data structure, it's important to know at any given time how many values we have on the size. This is actually going to be very important depending on the type of implementations that we have, because some implementations, which we'll discuss in a different video, have a very limited size. And finally, we can ask questions about the status of the data in the stack. So we have typically a method called isEmpty. It is obvious what it does. Maybe we could have a method that asks the opposite question. We would call it isFull. And definitely we have a method that displays the item that is at the top of the stack, and again, is called pick. So typically, when we talk about push, pop, isEmpty, and pick, it's understood that we're talking about stacks. So we assume immediately some type of behavior. So let's talk a little bit more in detail about the stack methods that we just described. So the push is the method that is used to add, therefore the parameter has to be the new object that is added onto the pile. And again, it's understood that it's going to be added on top of what we already have. This typically is a void method, but it could be implemented in a different way. The pop is the method that we use to remove, and again, very important. Notice that there are no parameters. Most remove will require a value, the value of the object that we are removing, or it will require a position, which is the position that we want to delete in our collection. Neither of those position nor value are required on the stack because there is only one element that we can delete, and it's the element at the top of the stack. And if we implement things correctly, we know exactly where that element is. So we remove the element that is at the top of the stack, and this method then returns the remove object. Pick also returns the object that is at the top of the stack, similar to remove, but it doesn't modify the stack. So it doesn't remove the object from the stack, simply says this is the value of the object that is at the top of the stack. And finally, it's empty. It's a Boolean method. It's trivial what it does. If the stack is empty, it returns true. Otherwise, it will return false. Be aware that there is a class in Java called stack, as you can see on the screen. So this is an implementation of basically the four methods: the push, the pop, the pick, and this empty, plus some other methods. But understand that this class is not commonly used when you try to implement a stack, because it uses a class that is a little bit old in Java, which is called a vector. So this is not the class that we're going to use when we implement stacks, but it will be a good idea if you spend some couple of minutes, go back to the Java API and look up the class stack. In a couple of minutes, I'm going to discuss two different ways of implementing the stack, and then there will be two separate videos for each of those two implementations. So the stack implementation, as I just told you, in general, we provide our own implementation for the stack. And typically, when we implement any collection, any large collection of data or values, there are basically two ways: arrays-based, which essentially uses an array, and reference-based, which means it's going to use some sort of linked list. So if we use the arrays base, the size of the stack is fixed because we have to create an array initially, and to do so we have to give it a certain size, so that's going to be fixed. It's not going to grow dynamically. And then we're going to have an integer, and that integer value is going to represent the index of the element in the array that represents the top of the stack. So we need to keep track of what is top of the stack. So instead of keeping other indexes, the only one that we need to keep is where the top of our stack is located. So I implemented an stack using a class, creating a class called myArrayStack. So I encourage you, after you finish watching this video and understand how the stack works, that you go to this video called myArrayStack and then look at the implementation of the stack using an array. The other option is to use references. So we're talking about linked list. So basically, to implement a stack, I use a linked list. Notice that this is very convenient because a linked list has a very defined beginning, right? And we have a reference to the first node on the list, right? We typically talk about the front of the list or the head of the list, and that's a reference to the first node. Well, think about that first node being the top of the list. So when we create the linked list to implement the stack, it's a given that we know where the top of the stack is going to be because it's going to be the reference to the first node. Again, I have created a second different video. That video is called My Linked Stack. So I encourage you, after you watch the array stack video, that you watch the linked stack video and compare the two implementations and decide the pros and the cons of each of those two. So finally, let's talk about some applications, real-life applications. So one that is very important is evaluating expressions in postfix and prefix notation. So if you don't know what these are different ways of representing expressions that use operators like addition, subtraction, square root, sine, cosine, logarithms, etc. And generally those are represented not in the form that we know, which is called in-fixed notation using parentheses, so on and so forth, but most of the time internal in the computer they're represented to use either prefix or postfix notation. If you're not familiar with these terms, I encourage you to go to the internet and search for postfix and prefix notation, and you will see many examples for that. Another important application of stacks in real life and in computing is backtracking. If you know anything about recursion, you know that there is a lot of backtracking in recursion, evaluating different methods or functions that has been temporarily postponed due to the recursion. Think about also the old problem of going into a maze and it has an entrance and you need to find an exit, and it's a series of right and left turns that you can take. Well, imagine yourself in a maze, so you're walking through and then you make a decision, you go to the right at any given time, and that leads to a dead end. So what do? You go backwards, right? You say, okay, I'm not going anywhere, so I need to go to the place where I decide to take a right, and instead of taking a right now, I'm going to take a left, or possibly go straight. You're going to make a different decision. So you're going back to the place to make a new decision. This is called backtracking. So if you can see, you can figure out a maze when you do it, let's say with pencil and paper, just try tracing a path until you find a dead end, and then what you do is just backtrack what you did, follow a different path, and if it doesn't work, you backtrack again, and you keep doing that until you finally find the exit to the maze. This is done with a stack by pushing elements into the stack, which in this case are going to be your decisions, going straight, making a right, making a left. And then you're going to be, every time you find a dead end, you're going to pop those decisions to go back to the point where you need to make a different decision. And finally, one of the most important transcendental applications for a stack is that stacks are used to run computers. Independent of their operating systems, there is something called the stack frame, and that keeps track of which record is being activated. Activation of a record means which instruction in your program, which command, which method, which function is actually being executed. And after that, how does it know to go to the next statement? When you call a function, when you call a method, how does it know that it's going to go back to that method? When you do recursion, how does it know to do the backtracking? Well, all of this is done basically using stacks. So stacks are not only commonly used to represent many things that happen in real life, but also is the way that computers run. So this concludes this presentation, and again, there are 2 videos that you should be watching with the array-based and the reference-based implementation for stacks.